In this tutorial, we will learn how to estimate an independent samples t-test in R, where an independent samples t-test is sometimes referred to as a between subjects t-test. So just briefly as some background, the independent samples t-test is part of a larger family of analyses aimed at comparing means. This particular statistical analysis is an inferential statistical analysis, and it's used to compare the means of two separate or independent groups. So for example, two different conditions or two different populations, consisting of cases, where cases could include individuals, employees, or however you conceptualize what a case is in your particular sample and population. Now, an important thing to note is that, again, we have two separate groups or two separate conditions or two separate populations of cases, and no case belongs to both of these groups. Hence this term independent samples t-test. Now, conventionally, an independent samples t-test will be appropriate when we have a categorical, meaning a nominal or an ordinal measurement scale predictor variable with just two levels or categories. So for example, your treatment and control conditions for a variable that assesses categorically whether someone was in the treatment or control condition of, let's say, a training, evaluation, research design. Now, in addition to the categorical predictor variable, when you have an independent samples t-test, the outcome variable will be of continuous nature, meaning that it's going to be on an either interval or ratio measurement scale. So for example, these could be scores on a test or something like that, or some type of assessment. So in the context of human resource management and within training evaluation specifically, the independent samples t-test is often appropriate for evaluating a post-test only with control group design. Now, as general background, there are different types of t-test, and we're just focusing on the independent samples t-test in this tutorial. But other examples of t-test include, for example, the paired samples t-test, which is sometimes called the matched pairs t-test or the dependent samples t-test. All right, so let's get started here. As you can see, we've got a data file that we can work with here today. This one happens to be called training evaluation underscore post control, with a capital T for training, a capital E for evaluation, a capital P for post, and a capital C for control. Now note here, as far as the variables we have access to here, one is a unique identifier employee variable here. And so this is an employee ID variable that helps us distinguish between the different cases. We don't technically need this today, but it's a helpful reminder that what we're dealing with today is a data set that's supposed to represent employees and whether they participated in the new training or an old training. And then, so that's our condition variable. Then we have our post-test variable here, which is after they participated in either the new training or the old training, everybody gets the same post-test assessment that's meant to evaluate something that they learned during the training. So what's important to note here is that this is a post-test only with control group design, which means that an independent samples t-test is appropriate. Here is our categorical predictor variable, and specifically this is nominal in nature. We have only two levels or categories for this condition categorical variable. You're either in the new training, you participate in the new training group or the old training group. No one participated in both of them. And then everybody participates in this post-test here as evidenced by this post-test variable. Okay, so be sure that you've saved this data file or whatever data file you have that contains your training evaluation data that's of type post-test only with control group design, and save that to a folder that you can subsequently set as your working directory. So for example, I have set this to my H drive R workshop folder. So you can see I've saved it in my H drive R workshop folder, and here is that file, and it is a .csv or comma separated values file. All right, so the next thing we're going to do is we're going to open up RStudio. Here I already have the interface open. I'm going to clear out what we have in the console here in terms of the R version history by going to Edit, Clear Console. And the next thing that we're going to do is go to File, New File, RScript. Again, that's File, New File, RScript from the dropdowns, and open up an RScript editor window so that we can make annotations and keep track of our script instead of just doing everything in the console. Again, our scripts will make things more reproducible. They make it easier to collaborate with others, and they can help you tell a story about decisions that you're making or interpretations. So using the hashtag annotation symbol here and to the right of it, I'm going to make a first annotation here, which is just going to remind us what the purpose of this tutorial is today, which is that we're going to learn how to compute an independent samples t-test, and this is from a post test only with control group design, specifically from the training evaluation design literature. All right, so the next thing that we're going to do is we need to set that working directory to that folder where we save that data file. To keep things simple, I'm just going to go to Session, Set Working Directory, Choose Directory, go down to my H drive. It's my R Workshop folder. You won't see your .csv or your data file appear here. You just have to trust that it's there in the particular folder. Click Open. And so here I have set my working directory. I'm actually going to, I get confirmation in my console here. I'm going to copy that text and I'm going to finish out this note here, set working directory. And I'm just going to paste that code below here, and this will just make it easier the next time that I open up this script. I don't have to do those drop-down menus again. Okay, the next thing I'm going to do is read in the data file. And I am going to read in the data file, and I'm going to name this data file data frame that I read in. I'm going to name it and assign it to an object that I'll call TD lowercase, just for training data. So TD, all lowercase there, just 2 letters. Use the left-handed arrow operator here so that we can assign the data frame that we're going to read in to this object that I've decided to call TD here. You could call it whatever you'd like. We're going to use the read.csv function from BaseR, and because it's from BaseR, we don't need to install an outside package to access it. And so the read.csv function, it's going to, assuming we've set our working directory and the file that we wish to read in exists within that working directory, all we need to do here is type in quotation marks within the parentheses and then type in the exact name of that data file, which here is training evaluation underscore post control. And so I'm just going to copy the exact name because that's kind of long. I don't want to have to remember that, including the capitalization and whether or not there's an underscore or a space. And so I want to make sure I get it just right. And all I need to do is make sure that I add the .csv file extension to the end here and within the quotation marks. All right, so hopefully this works. And so let's go ahead and run that line of code there. All right, so as you can see here, we have the TD data frame object that we created just now. You can see there's 50 observations or cases which correspond to 50 different employees. In this case, 25 employees participated in the new training program, 25 participated in the old training program, and they all have those post-test scores. Our goal here is to determine whether or not the mean scores on the post-test for those who participate in the new versus the old training program are the same or significantly different from each other. And so that's where the independent samples t-test comes in, which is an inferential statistical analysis, which allows us to make inferences about the underlying population from which a sample is drawn. Okay, so the first thing that we're going to need to do to use the ttest function that comes from the lessR package is we need to, if we haven't already, install and access the lessR package from R. And so in order to install a package, you can use the install packages, install.packages function. That's all lowercase, install.packages. And within the function parentheses and within quotation marks within those parentheses, type in the exact name of the package. And in this case, it's less, all lowercase, and then capital R. So all one word there, no space. I'm not going to install the package because I just recently did that, and it takes a little bit of time to install this package. It's a pretty big one. Not in the grand scheme of things, but relative to other R packages. And so for that reason, I'm going to skip this. But if you have never used the lessR package, you need to install it, or you haven't done so recently and think you might need an update to it, go ahead and run this line of code. I'm going to skip that though, because I have recently installed it. What I will do, and what you will need to do, is use the library function from BaseR and then type in within the parentheses as a sole parenthetical argument the exact name of that package. You don't need to put this in quotation marks there. You can just type in less capital R, so lessR right there. Do definitely run this line of code. You'll need to. And what's somewhat unusual about the lessR package here is that what you'll see is that typically when you get red font in your console, it's not a good sign. It's either a warning or error message. That is not the case with the lessR package. It just simply gives you some background information, who to contact, which is David Gerbing, Professor Gerbing at Portland State University School of Business. Here is his website. He developed the lessR package, and if you have any feedback, you can send it there. And you do see that there is a warning message that's separate down here, and this says that lessR was built under version 4.0.3 of R. I'm currently running 4.0.2. It should run just fine, but this is a note to me and a reminder that I should update the R version that I have running underneath RStudio. Okay, so assuming we were able to access the lessR package there, by using that library function, now we can, our library function, we can now access the functions that are within that lessR package. And so the next thing that we're going to do is we are just going to move right along to estimate our independent samples ttest. Okay, and this function name is really easy to remember. It is just ttest, all lowercase, all one word, ttest. And the first argument we're going to enter here is going to be our formula, or rather our equation or model that we wish to estimate here. You can think of it in any one of those terms. Okay, so the first thing that we do is we're going to enter our outcome variable, which, if you recall here, our outcome variable is post test with a capital P for post and capital T for test. So that's what we'll enter first here. So post test. Then we're going to enter the tilde symbol there. And so the tilde is useful. Is useful when we have an equation or a formula that we need to specify in R. So the way that you do this is that typically in R, when you're specifying an equation or a formula or specifically a model, then to the left of the tilde is going to come your outcome variable, and to the right of the tilde comes your predictor variable or predictor variables. In this case, we just have one outcome variable that's continuous in nature. These are the test scores, the post-test scores, and our predictor variable is categorical and specifically nominal, and it has just two levels. So when you have just two levels or categories for a predictor variable, and you have a continuous outcome, the independent samples t-test may be appropriate if you're interested in comparing means. Okay, so this is going to be where we enter to the right of the tilde symbol the condition variable there. And I'll actually go ahead and zoom in here. So hopefully you can see this, because I want to make sure that you see the tilde there, because sometimes it looks like a dash when it's a smaller font. So hopefully you can see this is the tilde that's visible there. And then we're going to type in the exact name of the condition variable, which is our predictor variable here with a capital C, it's condition. All right, the next argument is going to be, we will type in data equals, and then the exact name of the data frame object from which both of these variables came from, which is just TD. So I'll copy this from what we read in there. So it's TD, and you can paste it right there. Okay, so it's TD all lowercase there. And the next thing I want to do here is add an additional argument, which we don't technically need for the independent samples t-test with the t-test function from lessR, but I think it's nice to remind ourselves that we're not requesting a paired samples t-test. And so instead of paired equals false or true, we want paired equals false here, meaning we do not want a paired samples t-test. The data are not paired here. So just add in this third argument. I would suggest doing this out of habit. Paired equals false, so that we're requesting an independent samples t-test and not a paired samples t-test. I have a separate tutorial that shows how to do a paired samples t-test with this same function. All right, so we should be ready to run this now. So I'm going to go ahead and run the script right here. And what you might see here is that sometimes when your plot window is too small, because I've zoomed in so much here, I'm actually going to zoom back out since you had a chance to see what I mean by the tilde symbol. And now I'm going to rerun this script here, and it should work just fine. I'm going to make sure the plot window window is open large enough that it can render the plots that come default with the t-test function here. Okay. All right, so you should see something that looks like this in your plot window. We're not going to focus too much on this default plot that comes with it, but what you see here visually, it'll look a lot cleaner if you are looking at this through the zoom. If you click here, you can view it here, and you should see two distributions. And so one of our distributions is going to be for the new training condition, the other is for the old training condition, and these distributions of scores represent for the two populations or the two groups or the two conditions, their distribution of post-test scores. Okay, so let's set that aside. And what we're really interested in here is looking at the output that comes standard. There's quite a bit of output that comes standard in the t-test function here. And you'll see that it tells you right off the bat that you are comparing post-test scores across condition levels, new and old here for the new versus the old training condition. The first section we look at in the output of the t-test function is the describe, and this is where you get your descriptive statistics. And so it's organized very nicely here. So first we see the post-test scores for the condition new, so the new training condition here. And it'll tell us the number of missing values. We don't have any missing values. And it tells us the sample size for that particular condition or group, and it's 25. So 25 employees participate in the new training condition. What was their mean score on the post-test variable? It was 72, and let's say the post-test variable is out of 100. So it was 72.36 out of 100. What was the standard deviation of those scores? It was about 6.975. Now we can go down and, well, what were these descriptive statistics for the post-test scores for just those people that were in the old training condition, who just completed the old training program? Well, there's no missing data there. It's the same sample size of 25, but these are 25 independent people or distinct people that are not the same as the people that participated in the new training program, which is one of the reasons why we're using an independent samples t-test here. And the mean score is 61.32 with a standard deviation of about 9.15. So descriptively, we can see here that the means visually look different from each other. 72.36 for the new training condition and 61.32 for the old training condition in terms of their post-test scores. But our question is, can we treat this as a meaningful or statistical difference here? And that's where the independent samples t-test comes in, which again is an inferential statistical analysis that lets us infer whether or not that any difference we might have observed visually or descriptively here actually exists in the underlying population from which this sample of employees was drawn. So we can see right here that the mean difference of the post-test is, if you take 72.36 minus 61.32, you get 11.04, which is very nicely printed here for you. And you also get the weighted average standard deviation too, which we aren't really interested here for our purposes. So the next section you'll see is called assumptions, and this is where you can evaluate whether the statistical assumptions that should be met or satisfied for an independent samples t-test have been met or satisfied. Okay, and it's really nice that the t-test function from lessR points out right away that, note, these hypothesis tests can perform poorly, and the t-test is typically robust to violations of these assumptions. So use as heuristic guides instead of interpreting literally. We're going to interpret these literally just for the sake of learning them, but again, these tests can perform poorly, and these t-tests are typically robust to violations of these statistical assumptions. In other words, if these statistical assumptions don't appear to be met. So what is the first test that we're going to look at? Well, this is the assumption of a normal distribution for both of the populations. And here the two populations are going to be our two conditions or our two independent groups, which are the population of people that participate in the new training program versus the population of people who participate in the old training program, and whether each one of those distributions, which we saw visually here, are approximately a normal distribution. So that bell-shaped curve is essentially what we're looking for. Okay, so what we see, let's focus first on the training group, or the people that participated in the new training group condition. And we're going to be focusing on the statistical test that's called the Shapiro-Wilk normality test. And you get your W statistic here, 0.95. That by itself is not very meaningful, but what we are focused on here is the p-value, which is equal to 0.253. Now, these tests, you have to remember that what we're actually doing, our null hypothesis here is that the distribution is normal. So in fact, in order for us to find, at least statistically speaking, support for the fact that there is no deviation from normal here, we actually, in some sense, are seeking to accept or fail to reject the null hypothesis in this case, okay? And so let me go ahead and actually just paste this in so you can see this written down, the logic, because I think this is important to work through. So with statistical assumptions, I'll make a note here that that's what we're focusing on. And we'll start with the Shapiro-Wilk test. I'll add normality test here. Okay. So we're talking about the Shapiro-Wilk normality test. The Shapiro-Wilk normality test is used to test the null hypothesis that one distribution or a distribution is normal. So accordingly, if the p-value associated with the test statistic, which is W, is less than the conventional alpha level of 0.05, then we reject the null hypothesis and assume that the distribution is not normal. If, however, on the other hand, the p-value associated with the test statistic W is greater than 0.05, then we fail to reject the null hypothesis, which means that we do not have statistical evidence that the distribution is anything other than normal. In other words, if the p-value is equal to or greater than our alpha level of 0.05, then we can assume, based on the statistical test, that the variable is normally distributed, and then can feel pretty satisfied that we have met the statistical assumption of normality for that particular distribution. Okay, so this is a little bit I don't want to use the word backwards, but I'm going to go ahead and use it here. It's a little bit backwards than what we're going to be in terms of how we're interpreting statistical significance. And it's not really backwards. It just means that our null hypothesis is perhaps a little bit different than we're going to be thinking about when we get down to the inference section below, which is where we really focus on the independent samples t-test. Right now with the statistical assumptions section here, we're just trying to determine, is it even appropriate to use and interpret an independent samples t-test? Okay, so for the new training condition group, in terms of their post-test scores, what is the p-value associated with the W statistic for the Shapiro-Wilk normality test? It is 0.253. So that p-value is definitely greater than 0.05. So this means that we would fail to reject the null hypothesis that the distribution is normal. So what that means is we are failing to reject that the distribution is anything other than normal. So in this sense, we're getting some evidence here that it appears, at least for the new training group, post-test scores seem to have fall along a normal distribution for the most part. Let's come down here to the old training condition group and their post-test scores. We see their their W statistic here, and the p-value associated with that statistic is 0.62, which is also greater than or equal to 0.05, which is our conventional alpha cutoff level for statistical significance. And so here too, we would fail to reject the null hypothesis that the distribution is normal. So in other words, we're accepting that. We're saying, well, both of these distributions based on these two Shapiro-Wilk normality tests seem to be reasonably normal in terms of their distribution. Okay, so we seem to have found statistical evidence that supports the first statistical assumption of normal distributions for each of these populations or groups here. Okay, so moving right along, our next statistical assumption is going to involve the equality of variances, which is sometimes referred to as the homogeneity of variances test. Okay, and we're going to be using Levene's test, which is the second row below here. And what's really helpful is that both of these note what your null hypothesis is. So here it's the null hypothesis for Shapiro-Wilk is a normal distribution. For the equal variance test, the null hypothesis is that the variances are equal or homogenous, is another way of saying that. And so here you'll see the test statistic, which is negative 0.955, the degrees of freedom, which is 48. Those aren't really important here. What we do need to focus on is the p-value. And like I did before, I'm going to go ahead and paste in a written explanation of Levene's test here just to make sure that we understand it. And Levene's test, or the homogeneity of variance test, is commonly used to test the equality of variances assumption. The null hypothesis of this test, as I just mentioned, is that the variances are equal. Thus, if the p-value is less than the conventional alpha level of 0.05, then we would reject the null hypothesis and assume the variances are unequal, which means we would not meet that statistical assumption of equal variances. If, however, on the other hand, the p-value is equal to or less than 0.05, then we fail to reject the null hypothesis and assume that the variances are equal. In other words, the variances are homogeneous. So let's take a look and see what we found here. The p-value in terms of equal variances assumption is test, in Levene's test specifically, is 0.344. That is definitely greater than, and it is or equal to. So if this was exactly 0.05, it would be equal to, and it would also lead us to fail to reject that null hypothesis. But this is greater than 0.05, that conventional alpha level. And so therefore, we would fail to reject the null hypothesis that the variances are equal. In other words, we're accepting that the variances are equal here, at least statistically speaking. Now, if this had been less than 0.05, that would throw up a red flag for us and say, well, we may not have met the assumption of equal variances, in which case down below in the inference section, there's a different version of the t-test that we can interpret that doesn't have that assumption of equal variances. The same goes, however, for the Shapiro-Wilk test above. If either one of these have been less than 0.05, that should throw up a caution for us that perhaps we have not met the assumption of normality. Again, as noted above, the independent samples t-test tends to perform pretty well and tends to be pretty robust to any kind of violations of these statistical assumptions, but we should be cautious if we do get statistical evidence through the Shapiro-Wilk test or through the Levene's test if there is potentially a violation of one of these assumptions. Okay, so in our case, we look ready to go here, okay? So we're ready to go now and can feel pretty confident going into the infer section, which is where our inferential statistical analysis is where we're trying to make an inference about the underlying population. So we can assume that there were equal population variances of the post-test for each of the conditions, new versus old training condition. And so we'll read this first section here. If, however, you did not, if Levene's test was less than 0.05, then you would come down here and evaluate the t-test that appears down here. But we're going to do this first one here because we're assuming equal population variances or the homogeneity of variances. All right, so we will go ahead and if you want the information, you do have the standard error of the mean difference. You also get your t cutoff for the 95% range of variation. We're not going to focus on those here. Instead, we're going to focus primarily on this line here, which is the hypothesis test of zero mean difference. So our null hypothesis here is that the difference between the post-test scores on the new versus the old training condition, I should say the mean of the post-test scores on the new versus the old training condition, our null hypothesis is that that difference is zero, which is another way of saying that our null hypothesis is that the means are equivalent or equal to each other, okay? And so here is our t statistic, 4.798. Here are the degrees of freedom, which are 48, which for an independent samples t-test is just your sample size minus 2. And then we have our p-value associated with the t statistic here, which is where we get information about statistical significance. So we see the p-value is 0.000. It's not actually exactly 0 here. It's just a really small value that's slightly greater than 0. Okay, and so that's important. So in this case, we wouldn't typically write p is equal to 0. We would write p is less than 0.05, for example. It's less than the conventional alpha level, which brings me to my next point, which is the alpha level we've been using is the conventional cutoff for statistical significance is 0.05. Here we can see that, and this is a two-tailed test here, we can see that the p-value is less than 0.05. So what this means is we would reject the null hypothesis that the means are equal. Or in other words, we reject the null hypothesis that the difference between the two means is 0, which means that we are now concluding from a statistical perspective that there is a significant difference, statistically speaking, between the two means that we saw above here. Remember, we saw above the post-test score means for the new training condition versus the old, and we saw it was 72.36 versus 61.32, which was a mean difference of 11.04. And so what we're concluding here is that this value, which is the difference between these two means, it looks like statistically speaking, it is significantly different from 0, meaning that these two means on these post-test scores for these two independent populations or group seem to be significantly different from each other in the underlying population of employees from which this sample of employees was drawn. Okay, so that means we found statistically significant evidence here that there is a difference in means. Now it's important that we then go back and interpret it in the context of the actual described means or the observed means that we have for each condition. And so what we see is that it is in fact the new training condition that has a higher mean than the old training condition when it comes to those post-test scores. So this means that in terms of the post-test and whatever it was assessing about what people learned in the training, those people who participate in the new training program seem to perform significantly better, statistically speaking, on the post-test than those who participate in the old training programs. So this might give us, based on this post-test only with control group design, evidence that it seems to be that there's some evidence. We don't necessarily know if this is causal or not at this point, but there does seem to be some evidence that the new training program is better than the old training program with respect to whatever this post-test is measuring. Okay, so that we did find statistical significance. And when you find statistical significance, it's then customary to then interpret practical significance. If you do not find statistical significance, if this p-value associated with the t-value under the infer section here had been equal to 0.05 or greater than 0.05, then we would stop here and just conclude that those two means are not statistically different from each other. But we did find that they're statistically different from each other. So we're going to go down to the effect size section down here, which you can think of this as being evidence of practical significance that's contained here. What we're interested in is this, the standardized mean difference of the post-test, which conventionally this is referred to as Cohen's d. You can think of d as like the standardized difference or mean difference specifically. Well, here the standardized mean difference is 1.357. And so what does that mean in the grand scheme of things? Well, that is actually a pretty big whopping sized effect from most standards. And so let me actually paste in a little bit of a key here so you can see this visually, that in terms of how we describe Cohen's d descriptively, or their descriptors rather, in terms of the amount of practical significance, or the size of their effect, in other words, is small, medium, and large. And these are pretty coarse categories here, but these give you the idea. And conventionally, we'd say any value that's approximately about 0.2 or greater is going to be small, 0.5 or greater is going to be medium, and 0.8 or greater is going to be large. This value for Cohen's d is 1.357. That is definitely greater than 0.80. So this is large, or you might even say a very large effect here in terms of the standardized mean difference. So this is an indicator of practical significance here. Okay? And so these are the standards that I recommend starting out with. Depending on different contexts, though, these aren't meant to be absolute, and in different contexts, you might have different Cohen's d cutoffs that make more sense. But for our purposes, we'll just use these very conventional generic levels here, okay? And do note that the vertical bars here represent absolute value, okay? So the absolute value of 0.2, 0.5, and 0.8. All right, so what did we find here? We found that indeed there is a statistically significant difference in terms of the post-test scores between in terms of the means for those people who participated in the new training program versus the old training program, and specifically the advantage went to the new training program. So it looks like there seems to be some evidence here based on this post-test only with control group design that the new training program seems to outperform the old training program. And that's from a statistically significant perspective. And because we found statistically significant difference in those two means on the post-test for the two conditions, we then came down and looked at practical significance in the form of effect size and found that the Cohen's d standardized mean difference for those post-test scores was actually quite large, and definitely large at a minimum, because it exceeded 0.8 here, and it was 1.357. All right, well, that wraps up how you can actually interpret the independent samples t-test here. The next thing that we're going to move on to is that sometimes when you do find a statistically significant difference and much more so a practically significant difference, such as a very large effect here, then sometimes we'll want to create a data visualization and specifically a bar chart of the results. You don't need to do this. And I would caution you against creating any kind of data visualization when you don't find statistically significant finding, because you could risk someone just peeking at that bar chart or other type of data visualization and falsely concluding that there's differences because the bars in the bar chart are not the same height or length. And that might be inappropriate if in fact you found that there was actually, statistically speaking, those two means that the bars represent are not different from one another. And so again, use any kind of data visualization with caution. My general recommendation is only create them and display them and present them in reports or presentations if you do find at least a statistically significant difference or statistically significant association, depending on what type of analysis you're doing. Okay, so we're going to be using the BarChart function that also comes from the lessR package. So if you already accessed the lessR package above, then you will not need to do that again down here. But we're using the BarChart function from lessR, and it's BarChart with a capital B and a capital C, all one word there. Okay, and this will create a simple bar chart for us. And so the first argument is going to be x equals, and this is, you can think of x being our predictor variable, and this is going to be the variable that goes on the x-axis too by default. It's going to be our condition variable, and that's condition with a capital C. Then we type in y equals for our second argument, and that is going to be our post-test variable, which is capital P for post and capital T for test, all one word. I'm going to add a comma there to separate it from the third argument and actually put the third argument on the next row here, which is data equals TD. So type in the exact name of the data frame from which both of these two variables came from, your condition, your post-test variable there. Adding another comma to separate that third argument from the fourth argument. And now I'm going to add into some axis labels here. And we'll start with xlab equals for x-axis label, and just type in xlab equals and then quotation marks. Within the quotation marks, you can type whatever you want. What do you want to go on the x-axis? Well, remember the x-axis is going to have the training condition, which is two different independent groups or samples here. So you have your new training group versus your old training group. What do you want that axis to say? And I'm going to just say this is training condition. And then outside of the quotation marks, add another comma, and that separates out our last argument here, which let's do ylab equals and ylab equals quotation marks, and within the quotation marks, what do you want the y-axis to be displayed as in terms of its label or title? Let's go ahead and say mean of the post test. And I'll actually put a hyphen there, mean of the post test scores. Let's add that in. All right, so I'm gonna make sure my window is large enough here so that hopefully the whole plot will display without an error message. I'm gonna click run, highlight that code and click run. Okay, and so here you see we've got the training condition. This is the labels we provided for the x-axis, the y-axis, and you see that the bar for the new training condition is taller than the bar for the old training condition. We knew that already because the mean of post-test scores for the new training condition was greater descriptively than the old one. In fact, we found to a statistically significant extent these two means are different from one another based on our independent samples t-test. And we found out via Cohen's d and effect size and an indicator of practical significance as well, that this effect is actually quite large here, this difference between these two means. Okay, so that's kind of the default way you can display the chart there. There's other functions available, or arguments rather, available if you do question mark and the exact name of the function, so BarChart here, and you run that line of code there. So run it. Your help viewer window will appear here, and you'll get a bunch of other arguments that you can use to kind of finesse and style this. Although the lessR package has a separate function called style that you can precede different data visualizations with to add different aesthetics, colors, and so forth, eliminating grid lines, whatever it is that you like to do. But this is fine for our purposes. If you want to save this plot, you can save it as an image and specifically a .png file, or you could save it as a PDF. Or you could copy it to a clipboard like this and then paste it into a document you're working on or a presentation of some kind. All right, so this has been a tutorial on how to estimate an independent samples t-test using R. And again, the independent samples t-test is useful in the training context when we want to evaluate a training program in which we use a post-test only with control group research design. And so we walked through in terms of how to interpret statistical assumptions and whether or not we've met those statistical assumptions or violated them, as well as how to interpret the descriptive statistics inferential independent samples t-test statistic, as well as if we found statistical significance, whether we should move on to investigating the practical significance, and we did so using the standardized mean difference, which is commonly referred to as Cohen's d. So this wraps up the tutorial on independent samples t-test.